Hello everyone. Today we are going to look at RTL2UVM script which generates fully functional UVM test bench based on RTL file. We will go over the how the script will works. So the script requires only one input, which is RTL file. So we need to pass RTL file in a command line, and we need to choose which mode we want it, and optionally we can choose LLM as optionally. So how the script work is like it use PySlang, which is a lint tool, which extracts port information from the RTL, and it will help in generating a UVM sequence item, cover points, these things. So PySlang extracts port information like input port, output port, and parameter details, and with that it will generate a UVM test bench. So additionally, we can pass mode. We can select EDA Playground mode or Verilator mode. In EDA Playground mode, it will generate under TB folder. So in case of Verilator mode, it will generate under design module name underscore Verilator. So it will generate UVM test bench along with makefile in case of Verilator. So in EDA Playground, it will generate all UVM test bench components, and it will copy the RTL to the test bench folder. So in EDA Playground, once the test bench is generated, we can copy this generated test bench into EDAPlayground.com, and we can run UVM simulation. So I will show the demo on how to do that. And in case of Verilator, we need to just navigate to Verilator folder, and we need to type make. That's it. It will run UVM test bench in Verilator simulator. So for this Verilator, we need to have UVM compatible, Verilator compatible UVM library, so that it will run UVM in Verilator. Optionally, we have LLM switch, so it will generate UVM driver and UVM monitor logic as per now. So I'm planning to update to for scoreboard also. So currently it will generate UVM driver and UVM monitor. So here we use Google Gemini 2.0 Flash model. So we use Google Gemini model to generate UVM driver and monitor logic. So this is an overview. Let's see how we can see the demo. So this is a GitHub repository which has RTL2UVM. So I will give this link in the description. Now we will just clone the repo, and we will run with a simple design. So you can go through README also. So I have provided the information like how it works, and additionally this RTL2UVM script supports visualization feature. So which is nothing but like it will so whatever the UVM test bench it generates, it will map the all UVM test bench components in PNG format. So this is the one it generated for FIFO RTL design. So pretty much this all the component generated with the RTL2UVM script. So we can see that it generates driver sequencer agent, ENV sequence item, desktop, everything it will generate, and it will have this analysis port, and it will connect analysis port for coverage, scoreboard, and monitor. So it will. So once the test bench generated, it will create this PNG file which describes internal structure of UVM test bench, so that you can understand like what is connected to what. Okay. So we'll just go over the demo. Okay. So here I'm using a sample DUT, which is nothing but adder. So from VLS library. So this is simple test bench. We have two inputs and one output. Right. This is the design we are going to use here. So you can check in Makefile to see what are the commands we can use. So currently I'm going to generate EDA Playground. So in -t we need to pass a design file, and in -m, which is nothing but a mode. So here we are passing EDA Playground. So it will generate files which is EDA Playground compatible, and it will generate visualization PNG. So UVM testbench structure we can see it in the PNG. Let's see how it works. Right. It will just print out the all port list which we extracted using PySlang. So here it extracts clock, reset, input, two inputs and output, which we saw in design file, and it will generate all UVM components and objects. Additionally, it will create this graph. So you can see the test bench generated. So it will generate TB. Okay. Oh, yeah. So our DUT model name is adder. So we just use adder top, adder test, adder env agent, sequencer driver pretty much everything. We can see this is a design file and we interact with interface. Okay. So this is automatically generated by RTL2UVM.py script. Okay. So then it will generate all templates. We can just go over everything. So it will create a sequence item, interface, and everything it will create. So I'll just open on file. So based on the port information, it will generate this input output port, and it will create input output string, output to string, or convert to string, or convert to string, pretty much everything. And if we run without LLM switch, it won't generate UVM driver run phase. Okay. So it will generate new run everything, build phase, run phase, everything. So if you don't use LLM, so it won't create a driver logic. If you use LLM, so the LLM will generate UVM driver logic and everything will be taken care by LLM. So this is what it generates without LLM. Similarly, we can create for Verilator. Okay. So for Verilator, we can use this one. So enable coverage. So for Verilator, it will add design model name and underscore Verilator. So all Verilator compatible files will be created inside adder Verilator. So we can just go over the make file first. Okay. Okay. So here to this you need to have Verilator installed in your system, and you need to have Verilator compatible UVM library. So for my case, I have kept here. So I have given UVM root as UVM path, and pretty much everything it generates by the script, and it will automatically pick up the test and include directories, pretty much everything. Dogs, dump, if you want to make a dump, you can use this. If you have GTK wave, we can view the BCD file and everything. Yeah. So in case of Verilator, I think only major change I see is in sequencer. So in sequencer we need to pass both response and request for Verilator. Okay. So in case of EDA Playground, only one sequence item will be enough. So in order to run with Verilator, we need to make these changes, which is specific to Verilator. This is generated for Verilator. Okay, fine. So now we can generate a full UVM test bench using LLM. I will just generate it for I'll just generate for both LLM and EDA Playground. Let's see. So up to this point, it's generated by script. Now we got driver. Cool. Cool. So, okay, this is generated by LLM. So we can just go and see what it generates. Okay. So we can so as mentioned in diagram. So LLM UVM monitor and UVM driver are generated by LLM. So let's see what file it generated. Okay, just make it a big. Okay. So here, right? So without LLM, so we won't have this logic. So it will generate up to this point, and we have to add this logic. So in LLM, it has created this interface transaction, pin level transaction. So this is generated by LLM. So and I see things like yeah. I think it got printed everything. I think. Right, update the script for this. Yeah. So pretty much this is generated by LLM. So you can see this tag. So the thing is we need to remove this tag before we are running any simulation. Okay. We'll just take a look at the monitor. Yeah. So you see right. So this is generated by the script. Okay. So here we can see that we need to add our own monitor logic. So here, so I think without deleting the existing folder I have ran, so I just override. I think. Yes, we can delete and run. Let's check here. Okay, it got set. Yeah, looks like it got appended. So I'll remove this and do a run again. I think now we will see only one driver class. So with LLM, I think it took 7 seconds. I think without LLM, it will run less than seconds. It will basically just generate a template. So it's this for later. Okay. So we'll check the driver. I think yeah. So now you can see that we have only one class, so it's not overridden. Okay. So the thing is, with Gemini, I see this tag is getting generated when we are generating a entire file. So I think this we need to remove. Okay. This is generated by LLM. Okay. Similarly for UVM monitor, we just need to remove the tag. This got generated by, I think this entire file is generated by LLM. So we will look the script how we have given a prompt. Okay. So it has generated everything and we have copied DUT everything. So we'll just run a Verilator in the background. Okay. I think we're seeing some error. Okay. So it couldn't pick the UVM package. Okay. Let's just check the file. Okay. So yeah, I think I given a wrong path looks like. So I've just updated my UVM root path and I have renamed sample DUT into adder.sv so that it can it's easy to pick up for the later. I think, so the design name I have given adder.sv, so which is a module name. So I have renamed the sample DUT into adder.sv so that Verilator can pick up and run. Fine. So we need to okay, while it's running, we can go to the EDA Playground mode. So this for EDA Playground mode, we need to select mode as a EDA Playground. And design name, we need to pass it as adder.sv. Generated driver. Cool. Fine. Fine. So yeah, I think Verilator started run. I think it will take some time to complete. So we use EDA Playground to see how it works. Okay. So now file got generated under TB folder. As we see here, right? So UVM driver and UVM driver and UVM monitor are generated by LLM. This Gemini it's adds system verilog tag whenever it's create a file. So we just need to remove the tag. Okay. Same for monitor. So our EDA Playground compatible files generated here. we can just upload the sky in EDA Playground. Add the design here. So I think we need to move the top inside testbench.sv. Now we are good to go. Perfect. So in EDA compatible files, so it will generate or include testbench.sv. It will include everything and it will enable dump files, everything. So by default, it will provide added data. So the thing is we need to select run. So this got completed, simulation run got completed, and we can see coverage is 91. See, I will go through what we have given in a coverage. So the test bench generator, so I have given like have updated the script in such a way that it will just pick the input ports as a cover point, and I just added a auto bin max 2, and I just given a cross cover point. So feel free to add or update your cover point. So this is generated by the script. We can modify as you wish, and just add this comment and option.glue. So you can use all options you want. So that is thing. So the fact that we are seeing coverage, this indicates that there is a connection, there is successful connection between monitor and coverage file. Okay, so for now I have not running anything in a scoreboard. So I need to update with LLM how to. I need to see how to generate scoreboard logic by using LLM. So for now I have kept it as empty. So scoreboard it won't work. Okay, so I think we can check the waveform and see how it performs. The adder. So the design is simple. We just randomize the input one and input two, and we see whether it got added in out. That's it. And first we can check the clock and reset. Okay, so looks like clock is not driven. So UVM driver versus. So as we can see that it's not driving the reset signal. So I think maybe I can initialize it to 0. So whether it's generated by LLM. So if you fine tune the model, I think we can get what we need. For now, we need to manually edit this thing. And I think we are not seeing it. Let's just add input and output signals. I think we're getting some output. So this completely generated by this UVM driver and monitor is generated by LLM. Let's see how we have coded in RTL2UVM dot script. Okay. Let's see. Okay, the Verilator is still in run. Let's see. Let's quickly go over the RTL2UVM script. So I just removed my API, so we can add yours. Okay, fine. So here these are the necessary file which we need to import. PySlang is for linting, and this is Sharpsparse regress logging. This is for generative Google generative AI. We are using Gemini. Okay, so I'll just go to the main thing. Fine. So it will read the RTL file, and we're using PySlang. It will store DA2 design file. It will store all the uh, DA2 files, and we are using this scopy to collect port information. So I think we can see collect port data. So it will nothing but it will collect the input declarators, header direction, data type. So everything it will collect. So you can change this debug to info and see how PySlang is extracting input, and you can see how we are used in our script. Okay, so once we collect the port data, right, we will store it in some list in Python. So these are the lists we are using. So we store the port list, input list, declarators, only clock and reset, and only clock reset. So we are using this thing. Once we have collected the port, we are creating an interface file, sequence item, sequencer, driver, monitor agent scope, pretty much everything. And in case of Verilator mode, we will create a make file and some changes related to Verilator, like I said before. In case of UVM sequencer, we'll just see how it's creating an interface file. So interface file, like it will just from DV, it will take by naming convention, it will take DUT module name, and it will add interfaces. So it will in our case it will be adder underscore interface.sv. It's pretty much similar for everything. And sequence item, you can see. Okay. I'll just change this input to, in case of input, we change to rand. In case of output, we just change it to bit. Yeah. Main font driver. So in driver, we are just passing. So this is generated by. So this is by script. So this is driver name will contain DUT name plus driver. Yes, adder underscore driver. So this we are driver temp content, temporary content we are passing to the prompt. So I want LLM to create create a file which aligns with the rest of the file. So I am sharing the reference to the LLM. So I have used this to create a reference file. This design temporary content is a reference file. Okay, so the LLM enable is nothing but LLM switch is enabled, it will get activated. So in prompt, I'm just asking the LLM to create a UVM driver using this as a reference, so that it won't create random name and random interface name. So we need to get the interface which we set in the top. So for that purpose, I have added this temporary content and pass it to the prompt. So now I'm passing input ports, output ports, design file. Main thing is a design file, so that LLM will read DUT design file, and it will go through our template, and it will generate UVM driver with its own generator logic. Okay. So this is a prompt we are creating, and we are calling Gemini, which is the model I'm using. So yeah, here I think you can go to Google AI Studio and you can get your own API. It's free of cost. So and I'm using model as a Gemini 2.0 Flash, and I'm just capturing the response and returning this thing. So I'm storing this in a driver logic. So it's nothing but a Gemini generated driver logic, and we are writing inside L driver path is nothing but path to the driver, which is TB path, which is nothing but TB folder, and driver file name will be adder underscore driver.sp. Okay, so it will write in the file. Suppose if we don't enable LLM, so it will create our default template, and here we need to add our own logic. So if you enable LLM, LLM will add its logic based on the DUT design. So similar thing we do for monitor also. Monitor also we are using same method. We are creating a temporary file. We are passing the temporary file to the prompt, and we are passing this input and output everything. So your monitor logic temp is a reference file. So and we are calling Gemini, and we are passing the prompt. We are writing it to monitor file. So this is how you are using inside LLM. So for scoreboard, I tried to use LLM. So I just tried to pass, but it couldn't get the correct scoreboard logic. So I need to refine on this. Once I get it, I will update in my GitHub repository. So yeah. So I think we can achieve this. We can achieve what we want by fine tuning our LLM. I think Google Gemini we can fine tune so that we need to create our own data set so that it can train on that and we can use the model. I think it's pretty much achievable. Let's see. So once we generated file, and I think we need to create a make file for in case of Verilator mode, we need to create a make file. So I think here, so one thing is you need to update your UVM path so that Verilator can run. And pretty much it will take care of everything, TV name, DOT name, everything it can create in coverage flag. If you enable coverage, it will create with coverage. I think for coverage you need to give minus C. For coverage you need to give minus C switch so that it will done coverage. Okay. Once it's generated, last thing is it will generate a TB graph. So in TB graph we are using PyGraph this Python library, and we are using this to create a we are trying to use this tool to visualize the testbench is a script called generated. Okay, so you can go through this and you can add, if you want, you can just change anything. So it's pretty much what I have done. So I'm just trying to calculate time, which how much time it takes to generate a testbench. I think in case of manual, it take hours of time to generate basic testbench, but here we can generate within less than a minute. We can generate a testbench. So for now, the testbench we are generating has single agent, single ENV. So I'm planning to add multiple agents, multiple ENVs, and SOS to and testbench to support SOC level. So I need to work on script to support multiple ENVs and multiple agents. So for now, we just started with basic testbench and with LLM support. And I think once we fine tune LLM, we think we can get what we want. So fine tuning, we need to fine tune with our own data set. This is part of Google Gemini. So they have given us steps to fine tune a model. So we, in this case, we need to provide both instruction and output. So instruction will be create a test bench based on the design, and output we need to write a test bench. So we need to do it for multiple scenarios so that LLM can understand and can generate fully functional test bench for the design which is not trained. So I think this is for the further videos. For now, this is what I got. Thanks everyone.